Okay, here's a quick video for 10.1 practice A and 10.2 practice A. They're both pretty quick sections. It's just some probability stuff. And so we'll start on 10.1 practice A. They actually messed up on the problem. It's supposed to be you flip 3 coins, not you roll 3 dice. So you flip 3 coins. They want you to find the number of possible outcomes. So how many possible outcomes could happen if you flip 3 coins? I made them all up over here. You could get 3 heads. It's not likely, but you could. You could get 2 heads and then a tails. You can get a heads, then a tails, then another heads. You can get a heads and then 2 tails. Those are the 4 possibilities with a head first. Then you could get 3 tails. You get 2 tails and then a heads, and then a tails, a heads, and a tails, and then a tails with 2 heads. Those are all the 4 with tails first. So 8 total possibilities. That's just called a sample space. If you need a probability, you're going to need to know how many total options there are, how many total possibilities. Clown has 3 purple balloons labeled ABC, so purple A, purple B, and purple C. 3 yellow balloons labeled ABC, so yellow A, yellow B, and yellow C. And 3 turquoise balloons labeled ABC, turquoise A, turquoise B, and turquoise C. So he has 9 balloons. What would be the clown chosen at random? They want to know how many would there be? There'd be 9. You could have done 3 balloons times 3 colors. Here you got, two chances on the first coin, 2 chances on the second, 2 chances on the third. You multiply them, you get 8 chances. You can see how we got those answers. Now let's see. Your friend has 8 sweatshirts. Okay, has 8 total. Okay, the 3 sweatshirts are green, 1 is white, and 4 are blue. You forgot your sweatshirt, so your friend is going to bring one for you as well as one for himself. What's the probability that your friend will bring 2 blue ones? Okay, well, the chance that his first choice is blue is 4 out of 8. There's 4 blues, there's 8 total. So 4 out of 8, the chance that the first one is blue. But if he takes out a blue one, now there's only 3 blues left in the drawer. So the second choice, he's only got 3 possible blue ones, and there's only 7 left because he already pulled the one out for the first blue one. So there's 3 left, and there's 7 total. So you need to multiply those 2 fractions together to get the total probability. 4 over 8 can be reduced to 1/2. So 1 times 3 is 3, and 2 times 7 is 14. So 3/14 would be your probability that he would get 2 blue ones. All right, the estimated percentage of student GPA distribution is shown. Find the probability of each event. A student chosen at random has a GPA of at least 3. So that means 3.0 to 3.4 is in there, and 3.5 and 3.7 is in there, and 3.8 to 4.0. All 3 of these are above 3. At least 3 means above or equal to 3. So the 25%, the 12%, and the 7% are all at least 3. Adding them up gives you 44%, or you can make it a decimal as 0.44. What about a student chosen at random between 1.0 and 2.9? So not less than 1. So not 6. But we could go between 1 and 1.9. That's a possibility. And between 2 and 2.9. So 9 and 41, because we want to go between 1 and 2.9. So 9% plus 41% is 50%, or 0.50, or 0.5. Number 5, it says a bag has the same number of each of 4 different colored marbles. The marble is drawn, the color is recorded, and then the marble is placed back in the bag. So there's always 40 in the bag. This process is there's always the same number in the bag. There's always the same number. It's 40 draws. So the process is repeated. 40 marbles have been drawn. What this says, the table shows the results for which is the experimental probability. That's when you actually pull out the marbles, the experiment. So that's all these numbers. Okay, what's experimental probability of drawing the marble is the same as the theoretical probability. That would be the math part. So if you've got 40 draws and you've got 4 colors, then you should draw each color 10 times. Yeah, that's the math. The math says you should have about 10 for each color. You should have 10 for each color. The only one that actually got 10 was red. The other ones were different. So This is the theoretical probability. That's what it should be. This is the experimental probabilities. That's what you got when you actually did the experiment. So that's the difference between experimental and theoretical probability. 10.2, they want to know about independent and dependent events. So does one depend on another? So a box contains an assortment of tool items on clearance. You randomly choose a sale item, you look at it, and then you put it back in the box. Then you randomly choose another one. So you choose a hammer first, but you actually put it back in the box. So when you choose your plier second, the probability is still going to be out of the same amount because you put the hammer back. So since you put it back, that's an independent event. The second one's not going to matter what you got in the first one because you put it back. So that's independent. Cooler has assortment of juice boxes. You randomly choose a juice box and you drink it, so it's gone. You can't put it back if you drink it. Then you choose another one. So you choose a first juice box is orange, and then you choose a grape. This one is dependent. The probability of the grape will depend on what you pulled out because you took it out and you kept it out. Now there's less total. So that changes your probability when there's less total because you didn't put the first one back. So that's called a dependent event, when this probability is going to depend on this one because you took it out and kept it out. You're playing a game that requires rolling a dice twice. Use a sample space to determine whether rolling a 2 and then a 6 are independent. Well, they have to be independent because all numbers have the same amount of chance on each roll. So when you take the roll the first dice, the chance of getting a 2 is 1 out of 6. When you roll the second one, it's still going to be 1 out of 6 because there's only 1 6 on the dice. It's not like you can take the 2 off the dice or anything like that. So those are independent. Game show host picks contestants for the next game from an audience of 150. Randomly chooses a 30-year-old, then randomly chooses a 19-year-old. Use a sample space to determine whether the 30-year-old first are independent. No, that's not independent. That's dependent because you took the first person out and he's not going back into the audience. He's coming out to play the game. So he's already out to play the game. So now there's less in the audience. Now there's 149 in the audience when you pick the second person. So that's dependent event. It's not out of the same amount anymore. You kind of illustrate them here. A hat contains 10 pieces of paper, numbered 1 to 10. Find the probability of each pair of events occurring. So you randomly choose a number 1, then you put it back, you replace it, then you randomly choose a 10. So the probability of pulling out a 1 is 1 out of 10. There's 1 in there out of 10 pieces of paper. But you put it back in, so there's still 10 pieces of paper in there. So then when you reach in a second time, there's still one number 10 in there, and there's still 10 pieces in there. So 1 out of 10, 1 out of 10, they're the same probability. They're independent. Multiplying them together means it's going to be 1 out of 100 chance of getting a 1 and then getting a 10, or a 1% chance of getting that. But if you were to choose a 5 and you keep out the 5, and then you want to choose a 6, when you made your first choice, there was 1 5 out of 10 possibilities, but you kept the 5 out. So now when you reach it again, there's still only 1 6, but there's only 9 numbers in there. So it's actually a 1 out of 90 chance of getting a 5 and then a 6 if you keep the 5 out, which is like 0.11 or 1.1%. Teeny bit better chance, not a lot, but a teeny bit better. So that was number 5, A and B. That's how you can get independent and dependent events. Independent A, dependent B, because they changed. The probability the stock increases in value on Monday is 60%. When the stock increases in value on Monday, then the probability that the stock increases on Tuesday is 80%. So what's the probability that the stock increases in value on both Monday and Tuesday? So the 60% chance times the 80% chance of it happening back to back, you multiply together, it's a 48.48 or 48% chance of that happening. So that's a little video on probability 10.1 and 10.2 and what as independent and dependent events. So your job is to do the 2 puzzles.